Again, this is a more advanced question from Bristol University exam on analysis, of course, and we have a function f from positive numbers to positive numbers continues with 1 minus eta 0 less than fx over x squared less than 1 plus eta 0. I want to show that there is xi such that f of xi equals 2 when xi belongs to this interval. So, proof of that, I consider the interval AB where A is this number and B is this number here. Then, of course, f, since f is continuous on 0 infinity up to infinity, this is continuous on that interval, and we have this relation here. We have this relation from the hypothesis that's valid for every x that's more than 0. So for x equals a, we have f of a over a squared is more than 1 minus eta 0. So from here we have f of a is more than a squared times 1 minus eta 0. And again, from the same relation, we have f of a over a squared is less than 1 plus eta 0. So f of a is less than a squared times 1 plus eta 0. This is for a. We can write the corresponding expressions for b. So if we substitute b in the place of x, and finally from the relations above we have f of a is less than 1 plus 0 eta 0 times a squared, and this is 1 plus eta 0 square root of 2 over 1 plus eta 0 squared, and this is of course 2. So f of a is less than 2. In the same way we find f of b that's more than c, that's more than 1 plus 0 times b squared. So if you substitute b, you will have square root of 2 over 1 minus eta 0 squared, and this is again sorry, it's minus here, of course, so it's minus and it's cancelled and we have 2. What I have found is that f of a is less than 2 and f of b is more or equal than 2. Now, if f of a is 2 or f of b is 2, then xi equals a or xi equals b, because f of a equals 2, it means xi is exactly a and xi is exactly b. So what happens if we have that f of a is less than b, less than 2, and f of b is more than 2. So we don't have equality here, we have inequality. We don't have equality here, we have inequality. Then it's obvious from the intermediate value theorem that there is xi that belongs to AB such that f of xi equals 2. And this completes the question. Now we have the second part. You have fg continuous, g is increasing, the range of g is 0 to infinity, and there exists an eta 0 such that this relation here is true. I want to show that the range of f equals to 0 infinity. What does it mean? So to show that the range of f is 0 infinity, it means that if I take a random y that belongs to 0 infinity, so actually if I take a random y that's positive, always I can find xi that belongs to the domain of f such that f of xi equals y. So I need to find xi such that f of xi equals to y for every value of y that's positive. Now, how can I achieve that? Well, let's take a fixed y. So fix y, suppose that y is a constant number, then again we have 0, we have infinity, and somewhere here is y. But not only y, somewhere here is the number y over 1 minus eta 0, and somewhere here is the number y over 1 plus eta 0. And we have, of course, y over 1 plus eta 0 that's less than y over 1 minus eta 0, because the denominator here is bigger than the denominator here. Also the numerator is y and it is positive. So the order I have written here for the numbers is correct. Now, since my hypothesis says that the range of g equals to 0 infinity, it means that for every positive y I can find an x such that g of x equals to y. So I don't have one positive, I have this positive number, I have this positive number. So there exists an a and there exists a b such that there exists a positive a and there exists a positive b such that g of a equals to y over 1 plus eta 0 and g of b equals to y over 1 minus eta 0. Now, what's the relation between a and b? Because g is increasing and I have g of a less than g of b, I must have a less than b. Actually 0 less than a less than b. Now I know that f is continuous. I know that f is continuous, and I know that there exists a relation here for all x that are positive. I can substitute in that relation a and I can substitute b. For a, I will find f of a is less than 1 plus eta 0 times g of a, but if you substitute g of a here you will get y, and then from the above relation again I will get f of b is more than 1 minus eta 0 times g of b. And of course, if I substitute g of b with y over 1 minus eta 0, I will get y. So f of b is greater or equal than y. Now, since y is a constant for me, I create a new function. I set h of x equals f of x minus y. So, what happens here? I have h of a and h of b, and one of these is more than 0 and the other one is less than 0. So there exists, from Bolzano theorem or from intermediate value theorem, there exists xi that belongs to AB such that h of xi equals 0. Yes, but h of xi is f of xi minus y, so there is xi here such that f of xi equals y. Remember, we took a random y but fixed, and we found that for each y that we take there is xi in the domain of definition of f such that f of xi equals to y. Yeah, but it means from the definition of range that the range of f is 0 infinity. This proves completely the question. Now, if you have any answers, any opinions on the solution, or if you have any questions, you can email to and I will answer all your further questions if you have something like that, or if you have some opinion about making this solution easier, it would be well accepted. Thanks.